Hello, everyone. Welcome to week 7 of our course. I would like to congratulate all of you for doing well in prelims. And since we had our study break last week for our Family Day celebration, I hope you had recharged all your senses as we are going to start another term. We are now on midterm and we will be discussing Module 4 for this lecture recording. Okay, so kindly bear with me. I hope you had opened your module in advance so that we will be on the same page as we discuss our next topic for today's recording. So allow me to share with you guys my screen as we will be talking about electric current and Ohm's law for this recording. Okay, so all right, my screen is already there for you guys. Okay, so during prelims, we had discussed electrostatics. So when we say electrostatics, there is still no motion of the electrons yet, okay? And this time we will be discussing about electric current. That means that there is already the flow of electrons. There is already that motion of the electrons. That's why we have what we call as electricity. Okay, so with that, let's have this first, our very simple electric circuit. In our electric circuit, we have our basic components, which are the switch, the battery, or the source of energy, and our bulbs, which are our loads. Now, when we are going to draw this in a circuit diagram, the switch, the battery, the load have their corresponding symbols that we are going to use. All right, so for that electric circuit, our circuit diagram will look this way. Our switch is being represented by this symbol here, while our battery or the voltage source or the energy source is being represented with this. We already discussed this previously during our capacitors topic. The parallel lines are not equal. The longer line is positive and the shorter line is negative. While our loads are being represented by these zigzag lines, the loads will be the resistance of the current flow. Okay, so let us remember that for the electric potential between two unlike charges, the flow will always be from the higher potential to the lower potential. We already discussed that during potential difference because this causes the movement of a charge. So there must be the potential difference from higher to lower. There are free electrons while the switch is open. These free electrons are always moving in random motion. The random speeds are at an order of 10 to the 6 meter per second. And there is no net movement of charge across a cross section of a wire. So when we say cross section of a wire, that is the area within that wire. Okay, the movement is always going in this direction. If we have a wire, so say for example, this pencil, this is a wire. Okay, the motion of the electrons is always in this motion direction rather, but in the cross section area, the circular part of our wire, there is no net movement of charge because the charge always flow lengthwise and not here, not in the circular. Okay, so with that, what occurs in the wire when the circuit switch is closed? Okay, so this is our copper wire, a microscopic view of the copper wire. And the flow of electron is always lengthwise. There is no net movement along the diameter of the wire. Okay, so the electric field is going in that direction. Again, from higher potential to lower potential. Now, an electric field is established instantaneously At the speed of almost the speed of light, free electrons, while still randomly moving, immediately begin drifting due to the electric field. So there is the drift velocity. So when we say drift velocity, that is the velocity which is about 0.01 centimeter per second. So let us go back to our simple circuit. We have our switch, the battery, and the loads. The flow of electron is always from the higher potential to the lower potential, so it goes this way all throughout our circuit. So there must be the potential difference, okay? So as the electrons move from higher potential to lower potential, it moves from one load to another load. It loses its energy, and then when it comes back here to the voltage source, it regains its energy. So from higher potential to lower potential, the energy decreases, and when it comes back to the source of energy, it regains its energy and go again. So that is now electricity or electric current. There is the flow. So that is the conventional current. So by tradition, direction in which positive charges would flow. Direction is opposite of the electron flow. Okay, so the flow of electrons from positive to negative and the flow of electricity from positive to negative this way. It is opposite. All right. So what is required in order to have an electric current flow in a circuit? Of course, there must be the voltage source, the source of energy, either the battery or the outlet that we have in our homes, and the circuit must be closed. Okay. For a circuit to be closed, the switch must be open so that there will be flow of current in your circuit. Okay, since we are talking about batteries, this is the device that converts chemical energy to electricity. We already learned about chemical potential energy previously. So it needs potential energy difference, which is the voltage source. And the first battery was invented by Alessandro Volta. That's why we call it as a voltaic cell, and that's why we have the unit volt. Okay, so as mentioned before, a battery was big as a room, but now batteries are very small already. So for a battery, there must be the anode and the cathode. We have this in your chemistry class wherein sulfuric acid is an electrolyte and it separates into positive and negative ions. The positive ions of sulfuric acid goes to the negative electrode. That's why we call it as a cathode. And the negative ions from sulfuric acid goes to the positive electrode and we call it as the anode. Okay, so the anode has the higher potential while the cathode has the lower potential. So electric current is again the flow of electric charges, and it is being computed by the following formula. Electric current is equal to the charge per unit time. Okay? And charge, we already learned this. The unit is coulomb. The time is in second. Coulomb per second is equal to ampere. And this comes from the scientist Andre Ampere. And we will be talking about Ampere's law as we go on to this course. Okay, so the conventional current has a direction that the positive charges would have in the circuit. All right, so there are two types of currents, the direct current and the alternating current. The direct current, this is provided by the batteries, while alternating current is provided by power companies. So what we have at home in our outlet is actually the alternating current. And we do have AC to DC converters or the other way around. Now we have the ammeter. Ammeter is used to measure the flow of current and it must be placed in series connection with our loads. Okay? That is in contrast to the voltmeter. We're going to have voltmeter later. All right, so we have an example here. You are asked for the charge that flows through a cross-sectional area of a wire in 10 minutes if the ammeter measures a current of 5 milliamperes. Okay, let me try if I can use the... Okay, there you go. Very good. Okay, so our current has the formula I is equal to Q over T. All right. Sorry for my penmanship. Okay. Now you are asked for the charge. So just multiply, you can get the charge. The current is 5 milliamperes, and 5 milliamperes is 5 times 10 to the negative 3 amperes. All right. I will not include the unit anymore. Multiply that with 10 minutes. And 10 minutes is equal to, sorry guys, anaon lang nako. Okay, 10 minutes. 1 minute is equal to 60 seconds. Okay, so convert that into seconds. Okay, 1 minute is 60 seconds. All right. The time must be in seconds and the current must be in ampere. That's it. So 5 times 10 to the negative 3 amperes multiplied by 10 minutes times 60 seconds. You get our charge to be 3 columns. Okay, so that is very easy for you. All right, so we now move on to resistance. Resistance of an object, this is the resistance of an object to the flow of electric current. Okay, so it is being what do you call that? It is the ratio of the voltage and the current given by Ohm's law. Ohm's law was being proposed by George Ohm. So the voltage is equal to the current times the resistance. Okay, so for Ohm's law, we can compute for the voltage if we are given the current and the resistance, and vice versa for the other for the other variables. And since we're talking about Ohm's law, we have what we call as ohmic resistors. These are the devices that are there in our appliances. Okay, so if you still have the TV, the old models of TV, not the flat screen, there are the resistors there, and the resistors look like this. Okay, so these resistors have already given resistance value. They are put in the appliances in order to resist the flow of the current, so that it will regulate the flow of current all throughout the appliance. It will protect the appliance, okay, um from the sudden burst of energy, from the sudden flow of current. So the resistors will be there to protect. And the resistors regulate the current flow. The resistors converts the electrical energy into heat energy, because the resistors um, will become hot in as time passes by. Okay, so say for example, you are having your electric fan, you turn your electric fan on. In time, the electric fan will become hot at the back of it. Okay, because the resistors convert the electric energy to thermal energy, because it regulates the flow of electrons. Okay, so using the resistors, we can use the color coding in order to get the value of the resistance of the resistors. So we have our color coding in this legend. Okay, we have this given. I will This will be also given in your exam. Okay, so let us have this as our example for the resistors. All right, we have our yellow resistor. The first band is yellow, so yellow here is 4. So we have 4. Okay, let's draw something in here. Okay, so we have 4. Next band is purple. Purple from our table, it is 7. Oh, by the way, I am not going to give this table to you. You have to memorize this. We will have mnemonics later on. Okay? Red is 2. Okay? The third band of color will be our multiplier, which is times 10. And since red is 2, so we have times 10 to the 2. So that is our value for the resistance. And there is this last band, the band which is there at the last part at the other end of the resistor, that tells us the tolerance of our resistor. So it is gold, and gold is plus and minus 5%. So this is our tolerance. What is tolerance value? Okay, that means that our resistance is in this range. Okay, and we have our unit to be ohms. That means it is in this range. 4,700 plus and minus 5% of that. Okay, so let us have our calculator. 47 times 10 to the 2 is 4,700. Multiply that by 0.05 for 5%, so we have 235. So it could be 4,700 minus 235, it could be 4,465 to 4,935 ohms. That will be the range of the resistance value of that resistor. All right, so let us proceed to the next. Next, the first color is brown, and brown is 1. The second color is black, black is 0. The third is again 2, so we have times 10 to the 2. And our last band of color, let's just have it as gold again. So brown or gold? Gold, because this is brown. So let's just have that as gold. So we have again plus and minus 5% to be our tolerance value. So our resistance value for this resistor is 10 times 10 to the 2 plus and minus 5% ohms. And lastly, we have our red. Red is 2. Purple is 7, and then green is 5. So we have times 10 to the 5 this time. All right. And our tolerance value, this is gold again. For gold, plus and minus 5%. Okay, so for other tolerance values, it could be brown. Brown is plus and minus 1%. It could be red, plus and minus 2%. And it could also be silver, plus and minus 10%. So that's how you're going to use color coding in order to get the resistance values of our resistors. And as what I've said earlier, memorize this. I will not give you the table during the exam. Okay, so you may use these mnemonics. Black, brown, red, orange, yellow, green, blue, purple, gray, and white. Okay, so we have these mnemonics. Bad boys rape our young girls, but Patty gives away. Okay, so you can also use the other mnemonics that you are used to when you were still in junior high school or senior high school. I know you have this topic already. So, a battery provides energy. The battery pumps positive charges from low to high potential. Okay, so the resistors use up energy. When the current goes to the resistor, it goes to a lower potential. So here we can determine which point has a lower potential if our current is going in this direction with our three resistors. So would it be at point A or point B? Okay, so you can answer that now. And for this example, this is very easy. Just use Ohm's law. The answer is there. Just compute that for yourselves. All right, and this example, you have to think what will happen to the resistance if the voltage value doubles. Will the resistance also double, or will the resistance stay the same? Is the resistance a constant proportionality value, or is it not? Okay, so you have to think about that. All right, more about resistance. We can compute for the resistance of a material if we have the given resistivity, the length, as well as the cross-sectional area of the material. The resistivity is inherent to the material and it is given in tables. Okay, you have the table of values for that. Resistivity for copper, resistivity for other metals, and it is copper that we usually use for copper wires. Okay, so for metals, as the temperature increases, the resistance also increase. And at very low temperatures, the resistance can become zero. So the material can become superconductive. So for semiconductors, the opposite occurs. Now we, aside from the resistors, we also have a potentiometer, which is a variable resistor. Okay, so this is used for dimmers. When we say dimmers, that is for light. But when you want the light to become very bright or not so bright, you can turn the potentiometer as well as the fan speed controls. Okay, so the old models of fan have the turns, the knobs that we have. So that is making use of a potentiometer because it regulates the flow of current. Okay, that's why you can have the brightness, or you can adjust the brightness of the light by using the dimmers. You can also adjust the speed of the fan by turning the knob zero, 1, 2, 3, and so on. Okay, and this is the symbol for a potentiometer, just like the resistor, zigzag lines, and it has that arrow there. All right, so ammeter previously measures the current value, the voltmeter measures the voltage value, and it must be connected in parallel. For ammeter, it must be connected in series, but for voltmeter, it must be connected in parallel. Calculating for the power, power is equal to current times the voltage. P is equal to IV. All right. So just use Ohm's law. You can substitute V with IR, so you get this formula. Okay, and you can also substitute I with V over R. You can also get this formula. And we have an example here. The answers are given, so practice solving this. Okay, so since we are practicing solving, let us also practice solving this one. Take a screenshot or take a photo of our problem. We are going to solve this problem. Allow me to share with you my notes. Okay, let me check if I am there. All right, I'm there. Okay, so we have our circuit diagram. Previously, we had already discussed how to compute for the equivalent capacitance that are connected in series and parallel. Okay, so for capacitance, it will be opposite for capacitors. Okay, for no. For capacitors, it would be opposite for the resistors rather. For resistors that are connected in series, sorry. For resistors that are connected in series, this time in getting the equivalent resistance, REQ, you add all the resistance values. So KR1 plus R2 plus R3 and so on. Okay, so wait. So do not be confused with our capacitors. And for series connection, the voltage this time is equal, and so on. And for parallel connection, our our equivalent resistance is equal to 1 over R1 plus 1 over R2 and so on, 1 over Rn. And for parallel connection, our total voltage, no, oh, yeah. Our total voltage is equal. I will change for the series. That is for parallel, and for the series, it is the sum of all the voltages. V2 plus Vn. Okay. So again, as what I've said earlier, for resistors, it is opposite with that of the capacitors, okay? Because previously for capacitors, for series, the capacity equivalent capacitance is 1 over 1 over, and for parallel, you add all. And for series connection, the voltage value adds up, or the sum of all the voltages. And for parallel connection, they are equal. Okay, so let's now solve our circuit diagram. Okay, so we have our circuit diagram this way. All right, so this time we have two voltage sources. Okay, so this is our R1, R2, R3, and R4. Okay. R1 is 1 kilo ohms, R2 is 2.2 kilo ohms, R3 is 6.8 kilo ohms, R4 is 470 ohms. Take note, your units must be consistent. So you have to convert kilo ohms to ohms or convert ohms to kilo ohms. It depends on you. Okay, and we will arrive in the same answer. Now there are two voltage sources, 6 volts and 9 volts. So how are we going to do with that? Okay, you are asked to compute for the voltage in each resistance, and you are also asked to compute for all the current in each resistance. So first and foremost, we must get the equivalent resistance. Okay, so this is in series connection, so just add all the resistance values. Okay, so the equivalent resistance is equal to, you have 1 kilo ohm plus 2.2 kilo ohm plus 6.8 kilo ohms plus 470 ohms. You have to convert 470 ohms into kilo ohms. So 470 divide 1000. Wait, divide 1000. You have 0.47 kilo ohms. So the equivalent resistance for our circuit is 6.8 plus 2.2 plus 1. 10.47 kilo ohms. Now, since we have computed for the equivalent resistance, we can compute for our, what do you call this? We can compute for our current, for the overall current in our resistance, or in our circuit rather, or the total current. In getting the total current, we use the formula for Ohm's law. V is equal to IR. Okay, now V is equal to IR, so that means I is equal to V over R. Now this time, our total voltage must be the combination of the two voltages, which are the 6 and the 9 volts. Now, since our voltages are in this manner, they are arranged in this manner. This is positive, and this is negative, and this is negative. Positive and positive, they are they are connected together. So that means we are not going to add our voltage values, but we are going to subtract our voltage values. So we have here for our voltage 9 minus 6 volts, and our total, or our equivalent resistance is 10.47 kilo ohms We must have it in ohms because our unit for current is in ampere. So 10.47 times 1000, we have 10,470 ohms. Okay. So 3 divided by 10,470, we get our current to be 2 point, I will just round off, 2.87 times 10 to the negative 4 amperes. That is our total current. Now we are asked for the voltage values in each resistance and for the current values in each resistance. How are we going to solve for that one? Okay, so the total voltage is 3 volts. The total current is 2.87 times 10 to the negative 4 amperes. And the total resistance or equivalent resistance is 10,470 ohms. Okay, now, in getting the voltage value and current for each, you must take note that for series connection, the voltage is the total voltage is the sum of the voltages in each. Okay, so we can use the V is equal to IR for R1. Okay, V is equal to IR1. We already got the, wait guys. Oh, by the way, the current. Okay, so let us go back here. The current for our series connection is equal. Okay, so if we have total current is equal to I1 is equal to I2, and no, not plus, sorry, not plus, but equal to IN. Okay, that one. So the total current is equal to I1 is equal to I2 is equal to I3 and so on. So all the all the I's or all the currents in the resistors, in each resistor, they have equal, they have the same. And what current is that? It is 2.87 times 10 to the negative 4 amperes. Okay, so since we got that one now, 2.87 times 10 to the negative 4 amperes, our R1 is 1000 ohms. So I did not include the units anymore, but include your units in your computations is equal to 0.29 volts. This is for voltage value for the first resistor. For second resistor, the same formula. Okay, 2.87 times 10 to the negative 4. Second resistor, 2200 ohms. 2.87 times. Oh, wait, no. 0.87 times 10 to the negative 4. I rounded off, so maybe maglahi ang atong values. Okay, 0.63 volts. V3 will be IR3. I 2.87 times 10 to the negative 4. R3 is 6,800 ohms. So 2.87 times 10 to the negative 4 times 6,800, 1.95 volts. And lastly, for the fourth resistor, 2.87 times 10 to the negative 4 times 470 ohms. 2.87 is in the negative 4 times 470, 0.13 volts. And if we are going to add up all the voltage values, 0.13 plus 1.95 plus 0.63 plus 0.29, we will arrive at the same, at the answer for total voltage, which is 3 volts. Okay, the one that is here, 9 minus 6, is equal to 3 volts. All right, so we now have our voltage values. We now have our voltage values for resistor 1, resistor 2, resistor 3, and resistor 4. And our I, which is our, that would be our, ay nako, okay. And our total current will be equal to our I1, equal to our I2, equal to our I3. Dili na masuwatan, guys. Okay, I3 and equal to I4. That will be our current for each resistor. Current for each resistor, voltage for each resistor, and we can now complete our table. Okay, so practice answering your modules. Where am I now? All right. So I think that's it for this week 7 discussion. So practice answering the problems in your module, and it's all there. And if you have questions, you can message me on Canvas, okay? And I will get back to you as soon as I can. And kindly start working on your module before discussion hour every week. Okay, so see you again for our next topic for next week. So um, that's all for this discussion. Bye.